Hi, everybody. I've been asked to go over some physics questions to prepare academic team for this category. So I have, I think, 8 questions here that I'll walk through with you guys. I'm just going to zoom in to the first section here. And I guess before we start the first one, I'm not sure if you're given any sort of equation sheet or constant sheet, but if not, AP Physics has something that might be of good use to you. It includes the masses of proton, electron, neutron, speed of light, and some other constants, common units, as well as the prefixes too. So that's a resource for you to use if necessary. In addition, for one of these questions coming up, you would need the mass of the Earth and the radius of the Earth. So I just added those there at the bottom here. Okay, so the first one asks for two significant digits to determine in meters per second the velocity of a proton whose orbit has a radius of 0.25 meters and a magnetic field of zero point 0.5 Tesla. So the equation you'd want to use is R equals mv over qb, and B is magnetic field. Q is charge, M is mass, V is velocity. So I think all of them are pretty straightforward with the exception of Q. Q is charge, and B is magnetic field. So I just listed all of our givens here, and of course the charge of a proton is the same as an electron, just positive as opposed to negative. So I got that from the constants table over here. Once we list all of our givens, then it is just a matter of substituting in the work and solving for V. What I got was over here, this number, but then what you want to pay attention to, if we go, we go back to the question, two significant digits. So they're telling us how much we should round. So we would leave with or finish with 1.2 E7. And I'm showing here in green that we're really taking that decimal and we keep moving it until we get to 2 digits. So 1.2 is what this would round to. And that's all they're asking for. So I'm going to continue to go through these quickly, but definitely if you run into questions after watching this, you can always reach out to me. Okay, next one, we are looking for 3 significant digits to determine the meters per second, in meters per second, the minimum velocity of a satellite that is orbiting the Earth at an altitude of 150 kilometers. So the universal constant G is in meters, and if I go back over to that constant sheet, you can see it over here. The units are bizarre and not something you probably have to memorize, but meters cubed, kilograms, seconds squared, which really just means that in doing any calculation with G, I have to have any distance values in meters as well, or the units aren't going to work out right. So when they're giving us kilometers here, we definitely will have to convert that to meters. So going on to the equation, it is V equals the square root of G times the mass of the Earth divided by R. And the catch with this one is that if we're looking for velocity, the R is really the radius from the center of the Earth. So if you are given an altitude, you're adding that on to the radius of the Earth. And you can see that over here. So G is this constant. The mass of the Earth is here, 5.98 E24. And then we have the radius of the Earth plus the 150 kilometers. So I had to add the scientific notation here of 3 because the kilo means 1,000 or 3. So don't forget to do that. And once we plug all of that in, we get this number here. But again, going back to the wording, they want 3 significant digits. So we would round to the nearest 10th here, or 10, making this 7,820 meters per second. All right, we'll continue on from there. This next one is a momentum problem. So anytime there's any sort of collision, we're looking at momentum. And really, I didn't put it on here, but the overarching equation is simply that the initial momentum should equal the final momentum. And in general, momentum is mass times velocity. So at the beginning, the y block is just standing still. So it has no momentum. Mass times velocity would be 0. So the only thing I'm including is the mass of the little block, x, times its initial velocity. They collide and they stick together. So if they collide and stick together, we have to sum their masses together because now they're all one system. And then that would be times the final velocity. So the challenge to this one is that they're not giving us mass or initial velocity, and they're expecting us to manipulate the algebra. So here's where I'm just adding m plus 9m to get 10m, and then dividing that over to the other side. The masses will cancel. So m there cancels with m there, leaving us with VO over 10. And probably a better way to write that would be 1/10 of VO or 0.1 VO. And if you go back to the way they have the solution, they have it written in words, but it would still mean the same thing. Okay, moving on from there. The next one asks us to determine the speed in meters per second of a 15-kilogram ball thrown straight down from a height of 2.5 meters, which strikes the floor at a speed of 9 meters per second. So this would be considered a kinematics problem, vertical motion, or you could also look at it with kinetic and potential energies. The way I approached it here was with one of the motion equations. Final velocity squared equals initial velocity squared plus 2AD. We're given the final velocity. It's striking the floor at 9. Technically, it'd be a -9, but we're also squaring it, so it'll turn into an 81. We don't know the initial velocity, but then we have 2 times acceleration times distance. And both of these really need to be negative because of the fact that gravity is pulling us down, and the distance that the ball has fallen is also downward, as a downward vector. So those negatives really are going to turn into a positive, and that's why I have a plus 49 over here. As a last step of algebra, we would subtract the 49 over to the other side and then take the square root. And again, going back to the way they asked for it, they wanted 2 significant digits, so we would round here to 5.7 meters per second. Moving on. This problem is a force type problem, but it is one where the force is applied at an angle. So there are several steps, although the math is quite basic. There are several steps to consider in this one. So the first thing I would suggest doing is drawing a diagram to document all the forces. This one asks us to determine the coefficient of friction, which is the Greek letter mu, between, and I'm just going to get a pen here. So they're really asking us to find mu. It looks kind of like a cursive U between the blades of an 81 Newton sled. So if that is the weight of the sled, that is that downward force of gravity. So I've labeled that right here. That is pulled across a driveway at a constant speed. Anytime you see constant speed, that also tells us that the acceleration is 0. And by Newton's second law of motion, if the acceleration is 0, then net force will also have to be 0. So we're really looking for all the forces that we're documenting here to, in essence, cancel each other out. The net force that we find both vertically and horizontally will need to be 0. And then it goes on to say with a 38 Newton force exerted on the handle causing an angle of 42 degrees. So they're really pulling. As you can imagine, when you pull a sled, you're not going to pull it straight forward. That cord is going to cause you to pull it at an angle. So that applied force is right here, which means when we do that, we're really pulling forward and upward simultaneously. And that causes the variables FA in the x direction and FA in the y direction. We can use trig functions to find those force values, which is one of the steps we'll do next. But before we do, I also wanted to point out just, again, the reasoning behind this. So if the speed is constant, which was given to us here, then the net force will be 0 in the x direction. And I didn't label it earlier, but what I probably should have on here as well is the fact that the force of friction is opposing this motion. So the only forces along my x-axis are the applied force in the x direction and the force of friction. And if the net force between them needs to be 0, they're basically going to have to be equal. They're going to cancel each other out. Now, in the y direction, we can assume that the sled is not getting lifted off the ground. So there should be no motion in the y direction. And then that also means the sum in the vertical forces should also sum to 0. So this pull down of 81 newtons should be equal and opposite to the normal force plus the force applied in the y direction. And I think that part may be a little trickier to picture. So we'll look at the math that goes with that in a moment here. Oops. So there are 3 things that need to be done to find this. So like I mentioned, we have to find f(x) and f(y), which are really those trig functions. But then we also need to apply those numbers vertically and horizontally. Then at last, we can use the friction equation. So here's how the math works out. If I go back to just that simple trig function of sine, it is opposite over hypotenuse. And if I go back to my diagram, here's my angle of 42 degrees. Opposite would be FAY, hypotenuse would be 38. So I'm basically just using that trig function to say opposite over hypotenuse or FAY over 38. When I bring the 38 over to the other side, I can easily find that value. So I know right here, I'm just going to grab my pen again. So I know right here, FAY is the 25.43. Now I can change it to a cosine, which is going to change it to the adjacent side, which is the FAX, and that will turn out to be 28.24. Now, the one that I wanted to start with here was that x-axis relationship. If the applied force x is pulling to the right, friction is opposing that. So I can just automatically say, well, friction has to be equal and opposite to the applied force in the x direction. And I really don't have to do any additional math to determine that. So this number is important. I'll use this in the friction equation in a moment. So I'm going to circle that. Then we need to continue on from there. And if I can move the page, what I was saying earlier is that the forces in the y direction have to balance out too. So in the case of what we're looking at in the y direction, gravity was pointing downward, but the applied force and the friction force, or the normal force, were pointing upward. So I know 2 of these 3. I knew the weight of the object was 81. I found FAY from the trig function. So I was only missing the normal force, and I can simply subtract that over to find out that normal force. So these 2 values are really what I needed to get to. Once I have both of those, it is simple division. The frictional force divided by the normal force will give me the coefficient of friction. So that math is here. And then they wanted us to round it to 2 significant digits. So our final answer was 0.51. There are no units with coefficients of friction because it is simply a ratio of force over force. So no units are necessary there. All right, let's keep moving on from there. The next one, somewhere up here, is much shorter. This one asks us to find to 3 significant digits, determine the meters per second, in meters per second, the speed of light traveling in a substance whose index is 1.28. So it feels like there might not be enough here. They're only telling us one number. But the relationship tells us that the index, which is n, is equal to the speed of light in a vacuum divided by the speed in that new material. So if I were shining a laser light into a tank of water, the light, when it's traveling through air, is going to be nearly the speed it travels in a vacuum, since there aren't as many particles in the way. When the light passes into the water, the light actually slows down. And this simple division can show us that new velocity value. So all I'm doing is putting the 1.28 in for n. The speed of light in a vacuum is 3 times 10 to the 8. That is on the constant sheet I shared with you earlier. And that's just kind of a short one, easy to memorize one. And then it's just a matter of solving for v. So I brought the v over to the other side, divided by the 1.28, and that is all we needed to do for that one. All right, we'll keep moving on. And the next one is electric circuit. So with this one, it says to 3 significant digits, calculate the amps, in amps, the current. So current is a capital I variable of 3 resistors, resistor 1, resistor 2, and resistor 3 that are connected in parallel. And then, of course, a potential difference is a battery, so we know that voltage. Now, the trick to this kind is that really we have to know what kind of connection the circuit has, and they're telling us here it is parallel. So the diagram would look like this one here. Resistor 1, 2, and 3 are all in contact with the battery, and they are parallel to each other. The equation for resistors in parallel is a little bit on the messy side. It is an inverse relationship. So you're taking 1 over each of the resistors, but then you also have to take the inverse to get that final answer for equivalent resistance. So in essence, when I apply Ohm's law, what I really have to have is just one resistor that represents the whole circuit. And in parallel, it would be this equation to find that value. Once we know that, we can simply go back to Ohm's law, which is over here. As a side note, if instead this said series, that is the other type of connection for a circuit. And in series, resistance is a simple sum. So the Req is simply R1 plus R2, and so on. So that's just kind of a heads up if in case you get a problem like this where instead of parallel, it does say series. You would follow the same procedure, but instead of using this inverse relationship for parallel, it is a simple sum for series. Okay, so past that, once we have that equivalent resistance, like I said, we can just go straight to Ohm's law, V equals IR. They told us that the battery was 90. We found the equivalent resistance to be 17.14, and then it's just a simple matter of division here. All right, and I think we just have 1 or 2 to go. This one, we have to find with 2 significant digits, calculate in meters the minimum length. So even though they say the word length here, I would call that the variable d for distance, of a runway necessary for an airplane needing to reach 75 meters per second for takeoff. So this plane is speeding up so that it can get into the air. Alternately, you could be given a problem for landing as well. But the idea behind this is that once it makes it to the end of the runway, it hopefully is already in the air, or we're going to have a problem, right? So that 75 is really a final velocity. And then it goes on to tell us the engines can exert a uniform acceleration of 2.5 meters per second squared. So they're telling us pretty clearly here this isn't an acceleration. So that's simply a value of A. So like I was mentioning at the beginning, having an equation sheet will be handy, and there are a set of 3 or 4 motion equations that you should be comfortable with. And once you identify, well, this is a kinematics motion problem, decide which equation will be a best fit. And in this case, because we know final velocity and we're looking for distance, this equation is our best bet. Now, there is an assumption that has to be made. And that is in the fact that if you picture a plane getting ready to take off, at the very beginning, the plane's not moving, right? As passengers, we have to get into the plane. So the assumption is that we are starting from rest. So the initial velocity wasn't mentioned in the problem, but we can assume it's 0. And a lot of times you have to read into the problem to really decide on that variable. So since the initial velocity is 0, that term is basically gone. We can square the 75. 2 times 2.5 gives us the 5, and then divide to get distance. And again, they wanted this one in, I guess, 2 significant digits. Yep, 2 significant digits, so we had to round to 1,100 meters. All right, and that was the last one I had. So if anybody has any questions, feel free to reach out to me. I hope you found this helpful.